Hi, my name's Alyssa Wilk. I'm one of the senior maintainers of Envoy, as well as a senior staff engineer at Google. I've spent my last 11 years at Google working on the GFE team. The GFE is a Google front end. It's the HTTP proxy that front ends all of Google's web traffic. So everything from Gmail to ads to web search to cloud, the whole shebang. So doing this for 11 years, I've learned a lot about how to do proxying correctly and seen some spectacular failures when proxying goes wrong. And I kind of see it as my personal mission on Envoy to bring the GFE's level of resilience and reliability to the Envoy codebase. Essentially, as Google adopts Envoy, I want to make sure that if we're going to make mistakes, at least we're making new ones. So before I get into what we're doing with hardening Envoy, I want to talk a little bit about why we have to do this, right? We've been here all morning hearing about people who've been deploying Envoy and how they're running it as their edge proxy. It's great. Lyft's been using it for years. So what is there left to do? Well, first off, again, Lyft originally open sourced Envoy. They're behind AWS. So they have AWS as a front line of defense. But as we've heard today, there's more and more people using Envoy as an unprotected edge proxy. And this kind of increases your attack surface because there's different attack modes and more interesting targets for attacking. And then also, as Envoy is adopted as a cloud proxy, you have to worry about the case of untrusted and possibly malicious upstreams, as well as the control plane as an attack surface. People doing configs of death. So some of the work that I and my team, my larger team at Google, as well as the Envoy community have been doing, is trying to address this through a combination of software improvements, improving resilience against external attacks and hopefully accidental internal attacks, as well as test improvements. So improvements to Envoy's integration test, the integration test framework, our CI, our continuous integration, through adding fuzzing, and then coming soon, adding load testing. So starting with resilience against external attacks, because of course this is where things get really fun. My startup project on Envoy was trying to close the trickle attack vector. And what the trickle attack is, essentially, Envoy eagerly buffers from upstream. It really wants to have data ready for the clients to read as soon as the client is available, has available bandwidth to send it. But the problem is that means with very few resources, with a botnet and opening a number of connections that have large responses, you can pretty easily could cause Envoy to eagerly buffer, and then crash out of memory, which is obviously not optimal. So my starter project in Envoy was rewriting bits of the data plane based on a design by Harvey Tuch and Matt Klein to add in-memory buffer limits on every buffer down from the network connection buffer up to individual HTTP filters. And basically, as buffers fill up, they would signal the source of incoming data to back off using a combination of TCP congestion control and HTTP2 flow control. So coming back to this case of a fast upstream and a slow downstream, again, if you have this botnet aimed at Envoy and the downstream's reading really slowly, eventually the TCP socket buffer to downstream would fill up, the network connection buffer would fill up, and then Envoy would signal the router to either, for H2, stop acknowledging data, so the peer would stop sending data for that stream, or for HTTP 1.1 or TCP proxying, simply stop reading from the TCP socket and let TCP do its thing. And this is great, but it is woefully insufficient. All it does is make your attacker change their attack model. So the next thing we had to do was downstream circuit breaking. Again, you can have an upper bound on how much memory each stream can take. And so then your attacker just switches to opening many, many streams until, again, Envoy crashes out of memory. Or they keep opening new connections until your system runs out of file descriptors. And again, Envoy would crash. And this sort of attack mode has a really high potential for cascade failure. You can imagine it's not even a malicious botnet, right? If you run your envoys hot, you could just have an unusually high traffic spike. And your traffic spikes, your envoys are running hot. Some Envoy instance goes over its limit. It crashes. And then your front-end load balancer ends up spreading the rest of that load that used to go to that envoy to the rest of your cluster. And then one by one, the envoys get knocked over. And beyond that, it can be really hard to recover from this type of failure because even if the traffic spike is subsided, as your envoys come up, it's like a game of whack-a-mole, right? They come up, they sinkhole the incoming traffic, and they go right back down again. And then again, this is even more dangerous when coupled with Envoy's prior lack of keep alive timeouts. Envoy had timeouts on the request path if you had the buffer filter. If you're running without the buffer filter, it was pretty easy for, again, a malicious attacker to send a bunch of post requests and then have malicious use of more system resources than you want them to. And again, there was also a connection leak bug, which I'll get into later, which would, again, allow attackers to potentially use more system resources than we want them to. So Alyssa on my greater team implemented downstream circuit breaking, and now you can configure file descriptor limits and memory limits. And essentially, as you approach those FD limits, Envoy will stop accepting new connections. As you get near those memory bounds, Envoy stops accepting new streams. So now this combined with flow control gives you a bound on system resources. Right? You may not serve everything that you want to serve, right? Where you're not accepting, you're going to have high latency or timeouts. And where you're rejecting streams, you're going to have 500s. But having some number of 500s is certainly better than having a system-wide cascade failure. So that's resilience against external attacks. Moving on to internal attacks. One of the areas Google's put a lot of work into is protecting our backends, our upstreams, from our proxies. Right? It's really, really easy for a high-performance proxy to proxy enough requests that you're going to take out your backends. So one of the things we put a lot of work into is improving Envoy's load balancing. So the first thing we did is give Envoy a concept of priorities. In-house at Google, we tend to have primaries and failover clusters. So essentially, if something happens and you have traffic routing to your primary upstreams, and then they get overloaded, or you forget to change your config and you drain something, you want that traffic to gradually shift to the failovers with no interruption for user web browsing. Envoy is even more flexible than this because it allows an unbounded number of priorities. Essentially, priority 0 is your primaries, priority 1 is kind of concept of failovers, but you can have p equals 2, p equals 3, as many as you want to have. And again, the algorithms used to shift this traffic over, there's been a lot of thought put into them. They've worked at Google for well over a decade, making sure that as your upstream's going healthy, you shift traffic over really gradually and shift it back gradually. So you don't have queries kind of sloshing back and forth in a way that could overwhelm your upstreams and cause outages in the first place. There's been some work put in to improve fairness. So for example, an earlier iteration of one of the Envoy load balancers had a classic load balancing problem where it didn't have random offset. As Lyft discovered to the dismay, essentially what you can have is a coordinated fleet of envoys sending requests to upstream number 1 and then upstream number 2 and taking things out as they go along the line. And this is fairly easily fixed with random offset, but there's still a little bit of work that needs to be done if you have upstreams with very disparate weights. And that'll happen over the next year. And then finally, there's been a lot of work put into flexibility in load balancing. Envoy already had a great number of load balancers and different ways that you can route your traffic in terms of least request or round robin or weighted round robin. But Snow Pedersen, as he talked about earlier, also made it that we had flexibility in retry behaviors. Because again, if you're sending so much traffic through to your upstreams that you're overloading them, they're going to send back signals. And then the retry logic to try to actually send this query somewhere else may be different for Google than it is for Lyft, than it is for Square. So having this be an easily pluggable interface, as many things on Envoy are, so that everyone can put in their own custom business logic and do retries based on the particulars of their deployment is a really cool option that we've added to Envoy. Along with improvements to load balancing, we've added configuration safeguards. So the folks at Lyft upstreamed their proto-validation suite. So essentially, as people add new Envoy config, you can annotate it with bounds. So put a limit on how much memory a given string can take, or put a limit on how many entries a repeated field can have. And this allows us to do very, very low-cost, best effort avoidance of poison configs. Right? Everyone should absolutely validate customer config before they load it onto Envoys. It should not be trusting the Envoy config validation alone. But again, making sure that Envoy has some built-in resilience is fairly important. And then coming soon, hopefully in late Q4, if not early Q1, we're going to be adding the idea of reload and rollback tests. And I want to get in a little bit on why Google thinks this is really important. We learned this internally, unfortunately, due a particularly memorable outage. Like with Envoy, internal at Google, we tend to roll out features separate from the binary. So we config guard them, we flag guard them, we roll out the binary, and then we push a config that turn these features on in case they're buggy. What's really important is that all of these features are rollback safe. If you roll out a config, it doesn't work the way that you want, you need that rollback to actually reinstate prior behavior. And we had one particularly memorable instance where that didn't work, right? We rolled config out, it didn't work the way we wanted to, our operations team, like you do, rolled it back, and then the outage continued, right? And then you sit around dithering, well, was it actually the config that caused the problem? Was it something else? And then the only way to guarantee the prior behavior is to do a fleet-wide restart, right? Resetting every TCP connection, resetting every stream, it's really not enjoyable. And I've caught bugs in review, visually, that were sent up for review in upstream Envoy that were not rollback safe. So in-house, when we had this particular outage, we added best practices that when we're turning on a new feature via config, we do reload and rollback tests. So essentially an integration test where you send a request through, get a response back, and then use the internal equivalent of XDS to change the config to turn the feature on, send another request through and back, make sure that the behavior is changed, and then again, in one line of code, roll that back. and make sure that the original behavior is reinstated. Super important. And getting into that, there's a whole slew of improvements we've made to the Envoy integration test framework. And this is where I tend to geek out a bit. I love integration tests. This dates back to when I started at Google 11 years ago. I was a terrified noogler, and I was very well aware that any code I checked in could not just break Google Ads, but break all of Google. Right? So I invested a lot of time in the GFE's integration test framework, and I've been trying to bring these things one by one over to Envoy. So the first thing I did, again, starting on Envoy, I basically made it really easy to do what most people want to do when they're doing testing, is send a request and get a response. Right? We're testing a proxy. This should be pretty simple. So it's now 90% fewer lines of code for testing that happy path. We also added utilities to test end-to-end configuration. So again, most of our new features in Envoy are config guarded. People put them in filters. People put them as fields in the HTTP connection manager. So instead of doing a copy-paste edit of something like 40 lines of JSON, which, again, I always end up getting wrong, it's now 1 to 2 lines of C++ code, right? I just want to add this filter. Here's my filter config. I just want to tweak this particular field. And making it really easy for people to write integration tests. Because I've seen multiple PRs where people did comprehensive unit tests. Envoy has a really high bar for code coverage. But when I ask people to add integration tests, it turns out that the unit test didn't test the exact stream lifetime that actually happens in production. Right? So these unit tests ended up finding issues that weren't caught. The integration tests found issues that weren't caught by the unit tests. We made it a lot easier to do cross-protocol testing. So again, if you want to test full mesh of HTTP 1.1 downstream, H2 downstream, H1 upstream, H2 upstream, you can do it just by subclassing the appropriate class. And this is really important as people are messing around in the gRPC and adding trailers and making sure that as you do these upgrades and downgrades from HTTP 1 to H2, that things are working as they expect. We added an automated upstream, and this both helps, again, make the happy path of sending requests and response easier, but it also ends up fuzzing timing conditions. We found out at Google a lot of the time when you have crashing bugs, it's due to a specific timing where you disconnect at just the wrong moment, or you reset a stream at just the wrong moment. So having the timing of the client and the timing of the upstream completely decoupled in tests allows you to kind of fuzz these timing conditions and hopefully catch them over repeated CI runs. And then finally, improved debuggability. Sorry, skipping that. We made it a lot easier to debug the integration tests. So moving things out of the closure-based so you can use GDB. Michael on my Grader team did a lot of work to change the failure mode from infinite timeouts to fast fail timeouts telling you what went wrong. And then again, changing it so that a lot of the test failures inform you what you've done wrong and point you to documentation on how you might be able to fix it. And so all of these integration test improvements are kind of have their effect multiplied by improvements we've made to CI. So now every PR that goes out for review for Envoy gets run through address sanitizer, thread sanitizer, undefined behavior sanitizer, and client tidy. And these regularly catch issues before they're actually checked in. I can't tell you the number of PRs I've seen that passed a release build and failed one of the sanitizers. I don't want to admit how many PRs of my own have passed a release build but failed one of these sanitizers. They're really important. They catch a lot of bugs. Also, the increased CI runs do catch real production bugs of their own. We've had 2 issues I can remember offhand that were caught by CI by these increased runs because the more people we have developing on Envoy, the more times our CI gets executed. So the 2 I remember offhand, there was a backup bug, a race condition between L7 and L4, where essentially a user was doing a post, the upstream sent an early 400, closed the connection, and Envoy detected the connection close before it had read that 400. So it treated it as a server error and translated a 400, informing the user what they'd done wrong, into a 500. And Google takes 500s pretty seriously. This actually had been caught and filed by Istio, but it was caught by CI as well. And if we'd had more CI runs, CI would have caught it first. And there was another issue, this connection leak I mentioned earlier. And this was an issue where a classic error no bug, where Envoy would write to a closed socket, the kernel would inform Envoy that the route failed. We'd log the error no, and the very act of logging the error overwrote it if the log had flushed. Very rare race condition, maybe 1 in 5,000 times. But our CI caught it, we debugged it and fixed it. And this had been a bug that had been in Envoy since it was written, right? And that's now fixed. And along with all these CI improvements, we now have detailed instructions for reproducing and deflaking test failures. There's essentially a magic Bazel invocation you can run that brings it from 1 in 5,000 to 1 in 5 or so to make it a lot easier to debug. So again, I may wax on about integration tests. The problem with integration tests is they only actually catch issues you think to test. And this is where fuzzing comes in. So Harvey Tuch, again on my team, has put a ton of work into Envoy fuzzing. We now have 14 fuzzers covering a combination of untrusted code, like our HTTP and H2 codecs, as well as internal fuzzing, like config fuzzing. And these run as part of our CI, but they also run independently in cluster fuzz. Harvey's put a ton of work here. It's over 80 PRs and over 35 bug fixes. I started by going through git log to try to find exactly what fixes there were, and I gave up and asked Harvey because it was just too many, 35 plus. And these are serious bugs, right? These are bugs that could crash Envoy, that could cause deadlock, that would fail internal code assertions, essentially undefined behavior, that would allow buffer overflow. And goodness only knows what a malicious person could do with that. So it's really, really important. And the fuzzing is also an important part of Envoy's security story. Right, we have a really good team of maintainers doing code reviews for Envoy and paying a lot of attention to what gets checked in, but we also import libraries that other people write, right? And the maintainers don't pay a whole lot of attention as to what goes into HTTP parser or NGHTTP2, for example. So imagine someone getting some malicious code in NGHTTP2, and then Envoy imports that, right? We need some way of detecting that. And the fuzzers, again, throwing some combination of crafted and random data at Envoy are the sort of thing that would suss this sort of issue out. Along with fuzzing, again, we are working now on load testing. So Harvey and Josh Morantz are working with an external company, WeAmp, to try to have an upstream Envoy load testing harness. And this is super important, another way to catch bugs before they hit prod for Lyft or for any of the other Envoy users. In the last 6 months alone, despite all these improvements to integration tests, despite all these fuzzers, we've still had 6 different PRs that needed to be rolled back, right after check-in, a combination of crashes, CPU regressions, and straight-up buggy functional changes, right? I'd like us to be better here. And this doesn't even include bugs that we found more than a week or two later, which were too complicated to roll back and we essentially fixed in line, right? And some of these things really need to be uncovered with load testing, right? It's hard to figure out if something's going to be a CPU regression just by doing static code analysis. So having an external load testing harness where someone can run a load test on a clean PR for master and then run with their high risk, maybe this is causing CPU problems PR and see what the actual production impact is. It's a lot nicer than saying, hey guys at Lyft, do you mind smoke testing this for us, which is our current best practice. And again, there's a lot of things that you're only going to suss out with like load testing. Finding issues with downstream circuit breaking or finding things where different streams are interacting better. This is the sort of thing that you end up finding through load testing. And then finally, as much as I hate to admit it, which is why I didn't include it in my index slide, the really last line of defense here is adoption. While production is the last place you ever want to catch issues, it's bound to happen. One of the weirder bugs I've seen in my time at Google was an issue where it was only for users whose data was transparently proxied coming from one country running a specific version of OS X, right? You're not going to catch this sort of thing with load testing. You're not likely to catch it with fuzzing. This is the sort of thing you catch in prod. And the good news here is that Envoy is now used by dozens of companies. We've got tens of thousands of different deployments, tens of millions of QPS. I listed a bunch of people from the graduation proposal and from people who were speaking at EnvoyCon. But as an Envoy senior maintainer, I can tell you there's a lot more people than this using Envoy. I just don't know who's actually admitting it nowadays. Envoy has amazing uptake, right? And all of these different deployments are going to catch different bugs. So the more users Envoy has, the faster these issues are going to get found. And the larger our community is, the faster it's going to get fixed. So in closing, I want to thank all of you who are here who've already deployed Envoy or even Envoy Curious, because you're going to end up being a part of the reliability story. And I especially want to thank all the people who've contributed to the Envoy code base. We've had amazing progress hardening Envoy in the last year and a half, and I really look forward to seeing what we do in 2019. So thank you. Out of memory test?
Yeah, for example, when the program starts running, maybe a memory allocation can fail at the beginning and the middle at the end.
Yeah, so if the question was, do we run any out of memory tests? We do actually on import process run Envoy through memory sanitizer, MSAN, and I hope that we will get that upstreamed at some point. So yeah, we run that in-house, and when we catch things, we upstream fixes.
How much expertise would you say it takes to run Envoy, like not in front of the load balance or something? How much of this is now good defaults or just ready to go?
So the question of this is how much of running Envoy has good defaults? I can tell you, as I have not personally deployed Envoy at scale, I'm not really sure. I heard earlier today that someone did have a less than sensible default on how many upstreams. I think most of the defaults are good. And again, not everyone needs all of these features, right? If you're not regularly attacked, you may not need the downstream circuit breaking. But for certainly the big industry players regularly get hit by botnets, so they need that sort of thing implemented. And I would say the nice thing is that because Envoy has reloadable config, if you hit a point where all of a a sudden you're hit by your first botnet, and you're like, oh my God, what do I do? You can read up on this and then deploy that config rather than not really having a choice other than doing code fixes, which is going to have a much longer outage duration. Other questions? OK, great. Thank you.